Historically, attempts have been made to derive musical scales using ratios of small integers. In one of our labs, we tried to document how people felt about various ratios, and it was discovered that people tended to really like ratios of small integers. These are just 5 of the most common ones that come up when people are asked, like, what ratios do you like? So it's 1/1, 5/4, which is a major third in music. 4/3 would be a perfect fourth. 3/2 is a perfect fifth, and 5/3 would be sixth. But anyway, here's the sound of them, at least an approximation of them. You play C with E, so that's your major third. Perfect fourth, perfect fifth. So those are notes that people really like, and we just have to answer the questions about them. So it says, when any combination of these ratios is divided by the other ratios, that'll reduce to ratios of small integers, involving values of 10 or less when they're in reduced fraction form. So that is almost true. It's almost perfectly true. We just have to refer back to the lab on that topic. If I go back in time to this lab here, this is the one that's relevant. So on the first page of this lab, we were supposed to write in the ratios that correspond to those notes. And using this matrix, we were supposed to divide one fraction by another. So first, I divide 1/1 by 1/1, and you just get 1/1. Then you divide 5/4 by 5/4. That's going to be also 1/1. Anytime you divide a number by itself, you're going to get 1/1 for all these boxes. Okay, and then you had to use Symbolab or some kind of other calculator for getting the reduced ratios. So here I'll divide 5/4 by 1/1. I'll do that quickly on Symbolab. Okay, so there I created just kind of a complex fraction. I'm dividing a fraction by another fraction. Symbolab will tell me the reduced answer, which is 5/4. So basically, anytime you divide a number by 1, you get itself. So I can fill these in very quickly. Okay, but if we divide 4/3, which is a F, by 5/4, which is a E, that is one that's kind of unusual for this matrix here. Let's see what that is in Symbolab. Yeah, so we get 16/15. Now in this lab, we were supposed to color in ratios, and we were supposed to color them green if they were small integers, and yellow if they were questionable, and red if they were like bad combination. So see, all these are a good combination. These are things that people tend to like because they're small integer fractions. So they're all good here. I'll quickly fill in the rest of what it would be. 3/2 divided by 5/4. It's a G over a E. It is a minor third. 6/5 is what that one would be. A over E would be a perfect fourth, so that one's going to come out 4/3. C with E, 2 divided by 5/4 is 8/5, I guess. So all these are good. G with F would be 9/8. A with F would be 5/4. C with F is a perfect fifth, 3/2. A with G is 10/9. C with G, perfect fourth, 4/3. And C with A, minor third, 6/5. So these are all the fractions that you would have got. They are all at least 10 or less. So they're all good, and that's why that scale is such a perfect scale. The only one that's questionable is F with E. If you listen to them together, they're dissonant. Here's E with F. So that one's kind of questionable, so that's why I put it in yellow. But that's basically how you answer that question. I will tell you that on the real test, it's going to say involving values of 16 or less. So right now it's false because it says 10 or less, but on the real test it's going to be true because it's going to say 16 or less. So next one, statistically human listeners tend to like combinations of notes where the fundamental frequencies make small integer ratios with other notes. That is true. That was the point of Lab 5. A scale of few notes, such as the ones above, could have a high degree of mathematical perfection, but the trade-off is music generated from them is considered less interesting than if you use, for example, like all 12 notes, like many classical pieces do. They change keys all the time because people used to think like that was really interesting musically. This one's actually supposed to be true. More notes can be introduced to the scale shown above, which would add to musical possibilities, making the music generated more interesting. Trade-off, though, is that adding more notes will decrease the mathematical perfection of the ratios, and it leads to more potential for undesirable dissonances. That is true. That was the point of this lab that I was just talking about. So, if we added more notes beyond these, let's say like here, you add in a D of 9/8. So before, the scale just included these notes. Now we're going to be adding another note, which will be this D here. So when we add that, things get substantially worse. I'm going to copy all the ratios that we used in the previous example, and we just have to add a little bit. Most of it is going to remain the same. The only ones that are new now is going to be the D column and the D row. Everything else I could actually just copy from the previous table. So basically what we saw in the previous table was there was only one questionable problem, and that's when you match E with F. Okay, so here we got a 16/15, which was bad. All the other squares were good. The question is, what's going to happen with the D row and the D column? Like, will it create good ratios with the other notes or some questionable ones? Okay, so when you divide D by himself, that's just 1/1, so that's fine. But now let's try dividing the other notes by D. Let's try dividing E by D. What would we get when we divide 5/4 by 9/8? Let's check Symbolab. It comes out to 10/9, so not so bad so far. Okay, now let's try 4/3 divided by 9/8. 32/27. So that could be considered not nice. Let's see what 32/27 is as a decimal. It comes out to 1.185 repeating. And this is F divided by D. So let's say F4 divided by D4 makes that ratio. Now perhaps the ideal ratio that it should be is like a minor third. A minor third as a fraction would be 6/5. So if we divide 6/5, we get 1.200. Where this would be like the ideal way that we'd want to hear a minor third. And this is kind of like a little off, honestly, mathematically. And people can hear that it's off. So for that reason, I would put like, red or something in that square. So it doesn't make a good mathematical ratio with F. And that's the problem with introducing D. Okay, so Let's see if the other ones are good. 3 over 2 divided by 9/8 would make... let me do it on Symbolab. I can't do it in my head. What reduces to 4/3? Okay. So that's good. $40 over 27. Okay, so that one's not too nice either there. So this one turned out good. This one turned out pretty questionable there. This one's fine. And 2 over 9/8 will make 16 over 9, I think. Yeah, 16 over 9. So that you might say, okay, it's somewhat small numbers, but maybe questionable. And so this is what happens. Anytime you try to introduce more notes than just the standard 5, you're going to get these mathematical problems. So if we divide E4 by D4, it makes a ratio of 10 over 9. That's actually not that bad. So I wouldn't put that one as a problem. But this one, the F4 divided by D4, like that was a problem. Okay, dividing G4 by D4, that's not a problem. Comes out to 4/3. People like that ratio. But this one, dividing A4 by D4, that created 40 over 27, which is arguably a problem because of the size of the integers. And just to see what it would be, 40 over 27, it makes 1.481, which is like almost a perfect fifth. Perfect fifth would be 3 over 2, which is 1.50. This is what people want to hear, but this is what people would hear if they had used that key in their instrument. Here it says, though, what if we let D4 be 10 over 9 instead of 9 over 8? Would that, fix the problems? We're going to have the same table, basically. The only difference is, instead of using 9 over 8, we'll switch it now to 10 over 9 to see, okay, what if we did that? Would that fix the problem? Historically, they did this when they were making musical scales in the past. They said, okay, maybe 9 over 8 didn't work, but maybe 10 over 9 will. Okay, so here you get 10 over 9, which could be considered fine. But now you got to do 5/4 divided by 10/9. So let's do it on Symbolab. It makes 9/8, so that's not bad. Now let's do 4/3 divided by 10/9. Six fifths, not bad. Now 3/2 over 10/9. Uh-oh. 27 over 20. Not really good. So these ones are good. This one's good. But this one is, in my opinion, bad. Okay, then 5/3 over 10/9. 3/2, so that's fine. And then 2 over 10/9. 9/5. I would consider these good. Okay, but problems still occur, even with 10/9. The worst problem was that G4 over D4 makes 27 over 20 instead of the perfect 3 over 2. Let's see what 27 over 20 is as a decimal. It's 1.35, so actually it's supposed to be a perfect fourth. That's the goal when you're doing a G4 with D4. Perfect fourth would have been 4/3, which is 1.3 repeating. The next question says, can you find the percent error between one of these problems with the ideal ratio. So you got 32 over 27. They want to know what is it most similar to. You should divide it on calculator first. 1.185 repeating. And you should also find the decimal approximation of these ideal ratios too. So 10 over 9 on calculator is 1.1 repeating. 6 over 5 is going to be 1.20. 5 over 4 will be 1.25. 4 over 3 is 1.3 repeating. 3 over 2 is 1.5. So now you just have to look at these and see which one is closer to your ratio in question. I believe it is closest to the 6/5. What percent error does 32 over 27 make with that closest ideal ratio? So at this point, you want to do a percent error calculation with these two numbers. It's going to be your approximation minus the ideal over the ideal, and then just multiply by 100. So for our problem, we want 1.185 to be the approximation. You should keep as many digits as possible or reasonable in your calculation. All right, let's calculate that. You can even keep it like as a fraction if you want in the calculator, and then multiply by 100. So we're looking at 1.2% error, and there we go. Our next one says, what's wrong with 27 over 20? We determined that he was 1.35 as a decimal. So what's he closest to? He's closest to a perfect fourth, which is 1.333 repeating. So just do a percent error on those. And let's see what it is. .3% error. It might not seem like a big deal, but to very particular listeners of music, they may be able to tell that it's not quite right, you know. So that illustrates one of the problems inherent in music, like one of the mathematical problems that is impossible to overcome. That when you add more notes to your scale, you decrease the mathematical perfection. Okay. The next questions are about the scale we use today, which is a compromise of the past attempts that they had made to make a more perfect scale of notes, where you're trying to have a lot of possibilities, but you're trying to minimize the problems that occur. And so the 12-note scale was selected as a compromise. It works really well for being able to tune instruments easily and change keys very easily, because every note is the same ratio with the note below it for every note of the scale. It's pretty innovative, called the equal tempered scale. So we have these approximations that E4 over C4 will be given by a exponent there, 2 to the 4 over 12. And you want to find what that is as a decimal just with a calculator. 2 to the 4 over 12 is 1.2599 as a decimal. And so this is the equal tempered compromise, which is supposed to approximate the perfect ratio of 1.250. Then we can do 2 to the 5 over 12 to get what a perfect fourth would be in the equal tempered scale. It's 1.3348. This is supposed to approximate 4/3, which is 1.333 repeating. 2 to the 7/12 is our equal tempered perfect fifth. So that's 1.4983, and that one really comes close to the ideal, which is, of course, 1.5. And finally, A4 over C4 will be 2 to the 9/12, which is 1.6818. The ideal being 1.6 repeating. Okay, now those notes, the numerators, they come from the number of keys that the E4 is away from C4. So if you just look at a keyboard such as this, I'll say C is 0 notes above himself, C sharp is 1 note above himself, and 2 notes and 3 notes, so E is 4 notes above C4. F is 5 notes above C4, and so on. And that's where we're getting those numerator numbers. A4 is 9 notes above C4, and it's a 12-note scale. Okay, so we just have to do the same thing that we did in the previous question, find the percent error between these guys. So we're going to do 1.2599 with 1.25. This 0.79% error, which is fairly small. People don't mind so much the difference. Okay, now let's try 1.3348 with 1.33. It's 0.11% for that one. Very close. 0.11 for this as well. And 0.91%. Perfect. Now let's answer the questions about it. The equal tempered scale is effective because the ratios that E4, F4, G4, and A4 make with C4 are very close to the ideal mathematical ratios. That is true. We can see right here that the errors are quite small compared to what they would have been in the old way of doing things. Here we got more than 1% error. So that's the compromise. Even though the equal tempered scale has many practical advantages, it does not allow for there to be mathematically perfect small integer ratios between notes. That is true. The equal tempered scale allows for songs to be written and played in a wide variety of different keys. Totally true. Used to be you had to have your piano or your harpsichord or whatever tuned to a particular scale, such as trying to tune it to this, where you let the D be the only one that's off, and all the other notes were good. But it would only be good for playing songs in the key of C. Like, it wouldn't have been good for playing songs in the key of D, for example. So that was one reason for the compromise, is now with the equal tempered, they're bad. They're like equally bad no matter what key you play in. Okay, so equal tempered scale allows for instruments such as guitar to be more easily constructed and tuned and more versatile. Totally true. The equal tempered scale allows for 100% perfection between notes. That is not true.